Have you ever looked up at the night sky and imagined the solar system as a neat flat disk? Perhaps from school textbooks or simplified diagrams, you picture the planets orbiting the sun all on the same plane, like cars moving in lanes on a highway. But what if I told you the reality is far more fascinating and complex? What lies above and below this familiar plane challenges our understanding and opens a gateway to cosmic mysteries that could truly blow your mind. In this video, we're going to embark on a journey through the lesser-known three-dimensional structure of the solar system. We'll explore not only the well-known planets, but also the myriad of other objects, from icy bodies and asteroids to distant clouds of comets that swirl in paths wildly inclined to the main planetary plane. These celestial wanderers tell a story of cosmic interactions and gravitational dances that span billions of years and billions of miles. Prepare yourself for mind-expanding insights as we uncover what's really above and below the solar system and how this knowledge reshapes our understanding of the cosmos itself. The classical view, the ecliptic plane. Traditionally, when we study the solar system, we focus on the ecliptic plane, the imaginary flat surface defined by Earth's orbit around the Sun. Most of the 8 planets orbit the Sun very close to this plane, within a few degrees of inclination, which is why the solar system often appears like a cosmic vinyl record. This near coplanar arrangement is a consequence of how the solar system formed roughly 4.6 billion years ago. A giant molecular cloud collapsed under gravity, spinning faster as it contracted, forming a flattened protoplanetary disk. Within this disk, particles collided and stuck together, eventually forming the planets, moons, asteroids, and other bodies we observe today. The reality, a complex 3D structure. However, this neat flatness hides a complexity beneath the surface. Beyond the planets, many small bodies, including asteroids, comets, and dwarf planets, exhibit orbits highly inclined or even perpendicular to the ecliptic plane. These objects defy the simplistic flat model. Some asteroids in the asteroid belt tilt up to 30 degrees relative to the ecliptic. Beyond Neptune lies the Kuiper Belt, a ring of icy bodies with a wide spread in orbital inclinations. Even more intriguing is the distant Oort Cloud, a spherical shell of trillions of icy bodies surrounding the solar system, extending up to a light year away. Why this matters? Understanding the three-dimensional structure of the solar system is essential. It reveals the dynamic processes shaping our cosmic neighborhood, such as gravitational perturbations from passing stars, the influence of the Milky Way's tidal forces, and relics of the solar system's chaotic formation. This perspective also explains the origins of long-period comets and the potential threats posed by near-Earth objects with highly tilted orbits. Objects above and below, asteroids, comets, and the Kuiper Belt. The asteroid belt's inclined members. While most asteroids orbit in the ecliptic plane, there are significant populations with high inclination angles. These high-inclination asteroids can have orbits tilted up to 30 degrees or more, sometimes resulting from collisions or gravitational interactions that altered their original paths. These objects challenge the simplistic notion that all solar system debris is confined to a flat plane. The Kuiper Belt, a vast tilted ice ring beyond Neptune, the Kuiper Belt extends roughly from 30 to 55 astronomical units, AU, from the Sun. Unlike the asteroid belt, the Kuiper Belt is home to many objects with a broad range of orbital inclinations, some exceeding 30 degrees. The Kuiper Belt is the source region of many short-period comets, comets with orbital periods under 200 years, that periodically visit the inner solar system. The scattered disk and detached objects. Some Kuiper Belt objects, like Eris and Sedna, follow highly eccentric and inclined orbits, placing them far above or below the ecliptic plane. Their unusual orbits suggest past gravitational interactions, possibly with a yet undiscovered distant planet, Planet 9, or passing stars. The Oort Cloud, a spherical reservoir of icy bodies. What is the Oort Cloud? The Oort Cloud is a hypothesized spherical shell of icy objects enveloping the solar system from about 2,000 to 100,000 AU, 0.03 to 1.5 light-years. Proposed by astronomer Jan Oort in 1950, this cloud is believed to be the source of long-period comets, which take thousands or even millions of years to orbit the Sun. Why spherical, not flat? Unlike the flat ecliptic plane, the Oort cloud is nearly spherical. This is because gravitational interactions over billions of years, including perturbations from passing stars and the Milky Way's tidal forces, have randomized the orbits of these distant bodies. This spherical distribution means objects are found far above and below the solar system's main plane, truly above and below in the cosmic sense. How comets are sent into the inner solar system. Occasionally, the gravity of a nearby star passing close to the solar system disturbs the orbits of Oort cloud objects, nudging them toward the inner solar system. When these icy bodies get close enough to the Sun, their ices sublimate, forming spectacular glowing comas and tails, the comets we can observe from Earth. Gravitational influences, forces shaping above and below. The role of passing stars over the solar system's lifetime. Thousands of stars have passed close enough to exert gravitational tugs on the outer regions, particularly the Oort cloud. These perturbations are random in direction, causing the cloud's spherical shape and sending comets inward. The galactic tide. The Milky Way's gravitational field exerts a steady tidal force on the solar system, especially on the far-flung Oort cloud. This force helps to dislodge objects from stable orbits, contributing to the influx of long-period comets. Hypothetical planets and objects. Some astronomers hypothesize the existence of distant massive objects beyond Neptune, such as the proposed Planet 9, whose gravitational influence could explain the clustered orbits and inclinations of certain distant Kuiper Belt and scattered disk objects. A case study. The comet Hale-Bopp. In 1995, astronomers discovered comet Hale-Bopp, one of the most spectacular and brightest comets of the 20th century. It was a long-period comet originating from the Oort cloud, with an orbit highly inclined relative to the ecliptic. Hale-Bopp's exceptional brightness and long visibility period offered scientists a rare opportunity to study an ancient visitor from the fringes of the solar system. Its orbit and composition provided clues about the early solar system and the processes governing Oort cloud dynamics. The solar system is far more than a simple, flat plane of orbiting planets. It's a vast, three-dimensional environment filled with myriad objects moving in complex paths above and below the familiar ecliptic. Understanding this structure expands our knowledge about the origins and evolution of our cosmic neighborhood, the potential hazards posed by comets and asteroids, and the dynamic gravitational environment shaped by stars and galaxies. As we continue exploring and observing, we may uncover even more surprises lurking above and below our solar system, forever challenging and enriching our understanding of the universe.